Hello and welcome back to the Daily Space. I am still Dr. Pamela Gay, and I am still here to try and put science in your brains. But now I am not alone. With me are special guests, Planetary Science Institute researchers who are here to help me explain to you cool new news that's coming out of the polar regions of the moon and Vesta. As you know, I am actually an astronomer, not a planetary science. And so when cutting edge, kind of cool, and, well, really clickbaity results come out, I'm going to work to find experts to help you understand what's going on. Now, I could try and introduce them, but generally people do a better job introducing themselves. So with me is George at the top and Jordan at the bottom. And George, can you please introduce yourself to our audience?
Sure. Hi. So my real name is Georgina Kramer, but everybody calls me George. I've been a planetary scientist for over 12 years, and I graduated from University of Notre Dame. And I have pretty much been studying the moon pretty exclusively, actually. I try to dabble in some other like asteroids and Mercury a bit, but they keep throwing me back at the moon. But I like it.
If you're going to get thrown at something and thrown at the moon, well, I think that's kind of many astronauts' like dream job. So you're doing good. So Jordan, can you go ahead and introduce yourself?
Yeah, I'm Jordan Steckloff, and I've been a planetary scientist since about 2013, 2014. I also got my PhD in Indiana, but at Purdue University. And I dabble all over the solar system, but I do have some projects involving impacts into the moon, as well as Vesta, Ceres, Mercury, and numerous other small bodies across space.
So would I be correct in saying if it's been impacted, you're probably interested in it?
Somewhat, yeah. And not everything that needs to be impacted for it to be interesting. You can have landslides and things that fall apart without getting hit by something else.
That is all very true. Now, last week we had a pair of papers came out that I have since seen get turned into all manner of clickbait. The one that we're going to start with is the moon's south pole has been recently explored using gravity. And by looking at the differences in density from one point to another, there is a team of scientists now saying they think they've identified the location of a strange, large, high-mass object. Before I go any further, George, can you take over and tell us about this story?
I will do my best, Pam. Be sure to stop me and let me know if I have said a word that is not common for everybody, because I'm kind of notorious for that. So basically, the South Pole Aiken Basin is a huge basin that takes up like pretty much the bottom quarter of the far side of the moon. And it is the largest known, or at least everybody agrees that it's an impact basin or an impact crater in the solar system entirely. And in about the middle, a little offset, these authors have found a mass beneath it, and they've done that using gravity data, where the spacecraft basically, as it passed over South Pole Aiken, felt this tug at it that can't be explained by any topography high or something.
Now, we have lots of different objects in our solar system that are lumpy, bumpy, and smooth in all sorts of different ways. And our own moon, we already knew, wasn't an entirely symmetric object. Its core is offset towards us. And with all these different lumpy and bumpy things going on, what are the kinds of explanations that we can look for when looking at this kind of a signature in gravity data?
So the authors come up with two scenarios. And one of them, the one that they favor, is that there is a large, basically the core of some protoplanet or differentiated asteroid, meaning that it differentiated into a metallic core, a mantle of some sort, and a crust, floated around in space, got too close to the moon, and hit it. And probably, and then I'm conjecturing this part, as it hit, it since the crust and the mantle was a little bit more able to be burned away or broken up, that part blew up with South Pole Aiken's crust, but the metallic core just kind of went into the moon to some extent. It might have broken a little, but they are saying that the bulk of that thing probably went into the moon.
Now, the thing about this result that really gets to me is many of us have heard the phrase turtles all the way down to explain things that we can't really get to the root cause of. And in this case, it seems to be impacts all the way down. The moon is thought to have formed through the impact of a Mars-sized object against the planet Earth that created this big splash that coalesced into two bodies. The front side of the moon that we see today and a smaller body that later smacked into what is now the far side, often called, but erroneously called, the dark side of the moon. And now we're hearing that after a Mars-sized object hit Earth, another really large object hit the moon. Can you put all of this in context and explain if there are other possible explanations for what we're seeing out there?
So to me, it kind of makes sense that you could have, a large body hit the Earth, make a moon, and then there's going to be another large body that's going to be floating around. When the solar system was young, there was a lot more bodies out there, and they're gathering together. There was a lot of big bodies. So over time, gradually, those big bodies started hitting each other. And so it started becoming smaller bodies and smaller bodies that would do any of the impacting. So that part I'm okay with. But I get that, yeah, it's like impacts all the way down. But the alternative explanation that they give, and that I am not in agreement with, though, but I will say, is that I talked about a differentiated asteroid. Well, the moon differentiated too. And it did differentiate. It has a core that is probably metallic to some extent, at least. And it has a mantle, and it has a crust. And then the moon was a large enough body that the way the Earth still functions today, because it's a large enough body, it has volcanoes. It has things going on inside of the mantle still. In the moon's case, that stuff is probably dead, not geologically functioning anymore, but it was going on for at least a few 100 million years after it first formed.
And to cut you off for a second, these are the kinds of processes that on Earth led to us having mineable minerals where you end up with a stripe of iron, a stripe of bronze that can be mined.
Not really.
Okay.
That really, for that sort of a thing, you really need to have the Earth, which is like where the tectonics, they keep recycling over and over and over and over again, so that the mineral or the elements like gold or platinum that don't want to enter into any mineral start getting kind of put together off to the side, and then they wind up coming up and being exposed, and everyone's happy and makes money. On the moon, it was probably more like a one-time kind of thing. There wasn't recycling, but there was inside the mantle down to maybe 200 or so kilometers. There was some melting that occurred, and that allowed for some volcanism to occur. And there happened to be other large impacts that hit that we are very familiar with on the near side. They're the Mare basalts, the dark places that make up the man in the moon and other things. Those are the end result of that melting inside of the mantle and the volcanism that came up into these depressions that were created. So there were low-lying areas, so the lava, the magma comes up and it becomes basalt material. So some of that melted mantle material is denser than the crust that sits on the top of the moon. But it was able to rise because there was probably gases, and also that it was much hotter. So it would rise up and it would actually flow. Not all of it made it. So you can get some dense things still down inside inside the moon because it melted and then it never made it to the surface, and it solidified and it's denser.
So gluten-free space, sorry, I'm appearing on the screen twice. Gluten-free space, when one of our audience members is asking, could the mass under the surface actually be a mantle plume? They're known to have higher gravity, and it sounds like that's what you're getting at. And again, I'm an astronomer and a data scientist. geology is one of those things that is why I have you here. So feel free to correct me.
Oh, well, so that's a good question, and it's close. It gets a little bit more complicated than that, but I mean, yes, I see mantle plumes that we think of on Earth. They're coming actually from the core mantle interface, and they're just super hot, and they go through several hundreds of kilometers and go all the way to the surface. So in this case, it's more like, you're thinking of a more shallow sort of thing, and there's just a melting of material. And what's kind of neat is inside, think of a magma chamber. It's like a big magma chamber, okay? And inside of this magma chamber, the crystals start to crystallize out, and these things that crystallize out are they're denser than the remaining magma, and they fall to the bottom. And then they crystallize out until finally the magma's like, that's it, I'm out of here. And it blows up to the surface and it flows as lava. But like I said, those crystals that fell out, they were denser. So they get left behind, and we call them cumulates because they accumulated. So those would be the signatures and this is what the authors put forward as possibility, that those could be the signature, gravity signature that they're seeing. So we put it as a possibility, but not a likely one, actually.
And the question that I keep getting is, could it be a monolith or a buried UFO? And here I think I can confidently say that it is statistically approaching zero that either of those possibilities are true, and I feel confident in saying it is not a monolith or a buried UFO. But if we wanted to test all of these possible options and figure out exactly what is it that's going on, do we have the capacity with modern day technology, or is this just something that's literally out of our reach to sort out?
So the answer to that is a yes and no. So the kind of easiest way that you could think of to go and say, hey, what is this thing down there that's causing so much gravity, would be to go and dig. But the authors are saying it's 300 kilometers down. And that's really deep. On Earth, we've only been able to get 5 kilometers down. And that's using resources on Earth that we have plenty, and we can just get whenever we want. If we're up on the moon and we're trying to drill into the moon, not a lot of water to cool our drill, there's going to be problems. But we could go to the moon and bring equipment, better, higher sensitivity gravity equipment, for instance, which would be able to make more accurate measurements and get a better estimate of the extent and depth and how dense this object is. But we'd have to go run a ground penetrating radar over it or something.
Which sounds awesome, and I totally think we need to do.
And I will push that JPR, no problem.
And I will be there to help with any citizen science efforts or database monkey work you need. So we have a couple questions from the audience before we go over to our Vesta story. Henny's Vorverp asks, how could something so big hit the moon and not Earth? And can they tell how fast it was going?
It's a good question. I think that they could tell how fast it was going if they knew that for sure it was a differentiated meteorite. They knew how big it was and how dense it was and how deep it went. So, but because all of those are estimates to begin with, that estimate on how fast it was going, we kind of lose. But we could also make conjectures based on how fast these sort of asteroids move through the solar system on a regular basis. Why didn't it hit the Earth? Because the moon was there. It probably wouldn't have hit anything, actually, if the moon wasn't there. The speed it was traveling, it probably wouldn't have been, the Earth probably wouldn't have tried to suck it in or anything.
And this is a really important point, that while the Earth is bigger than the moon, with the rate that things go flying through our solar system, it's not the mass that matters, it's the surface area available to hit. So yeah, we probably in the grand scheme of the universe do get hit more often than the moon, most of it melting, burning up, whatever adverb you want to use in the atmosphere. But that's only because we have a larger surface area for things to hit. It's like having a larger target on our backs. We literally are a larger target. So final question coming in from Larry Weird, and you can keep asking questions. I just want to move to the next story. Would the low gravity make drilling easier or harder on the moon? Is the underground temperature lower on the moon than on Earth?
So I'm not actually someone who drills myself, but it's my understanding that the temperature that you're dealing with is the drill interfacing with the rock. So it's that drill is having problems getting through just the crust of the rock of the crust. So if it made it all the way down to the mantle, like on Earth, it made it all the way down to the mantle and it got that hot, it's going to be probably less of a problem than just getting through the crust and all the heat generated.
Yeah, and here it's the heat generated by the drilling unit, not the heat generated by the moon's interior.
Exactly, yeah.
So there's so many things that affect drilling on Earth. Luckily, not all of them affect the moon, but that dominant effect of drilling generates heat. Don't touch your drill bit after you've been drilling for a while.
But yeah, I've learned that the hard way.
yeah, it's something that affects all of us. Okay, Jordan, you're up next. Vesta, it's the weird asteroid in the inner part of the asteroid belt that Dawn visited because it had the probability of being an extremely dry world. And when we got there, we realized it was also a squished world. It was a world that was probably once more or less round, but took one for the team, and as a result, got squished into a really weird shape. Can you tell us more and tell us about the new theories that people have and how they can be tested that explain how it got so messed up?
Sure. So Vesta is one of those protoplanets that we were just talking about. It's about 260 kilometers in radius, so figure about 300 or 400 miles across. And it looks like it's round-ish. Looks like it used to be round. And we knew that it had been smacked around a bit. So the Vesta was the target of the Dawn spacecraft. But before Dawn even got there, we were able to look at it with Earth-based telescopes, such as the Hubble. And what we saw is that there was this flattened bit at the south pole of Vesta with a mountain in the middle. It looked like a giant impact crater that had a central peak. And what that means is that usually when we think of rock as, well, literally rock hard.
Yeah.
But when we're talking about impact processes where things are moving at miles per second or tens of kilometers per second, rock is no longer rock hard. It acts like almost like a liquid. It splashes. And so this central peak that we could see from the Earth is actually the central splash that got frozen in place. So we knew that Vesta had taken a pretty big hit before we got there. And when the Dawn spacecraft arrived, what we saw was that there wasn't one impact there, but there were actually two. There was the one we saw from the Earth called the Rhea Silvia Impact Basin, but that happened to be superimposed on top of an even older impact basin called Venonea. And when we say these are basins, these are massive impact craters that form a crater nearly the size of the object. If it was just a little bit larger, it probably could have destroyed the body entirely. And so we've known about this. And it turns out that not only have we known about this crater at the south pole of Vesta, but we think we actually have pieces of the debris that was formed when this crater formed. And the reason we think we have debris is, well, when you hit one asteroid with another asteroid, you make a whole bunch of other asteroids. And these asteroids get thrown all over the solar system, and periodically one of them hits the Earth. And if it falls and someone finds it, we now have a piece of Vesta. And it turns out we think we have a whole bunch of these. There's a whole class of meteorites called the HEDs. That stands for Howardite, Eucharite, Diogenite meteorites. And it's long been thought that these were all pieces of Vesta. And after the Dawn mission, the consensus is that, yeah, these actually came from that exact body. So it's kind of cool to think that not only do we have pieces of Vesta, but because it was such a big impact basin, and because Vesta was one of those differentiated bodies, not only do we have pieces of Vesta, but we have pieces of different parts of Vesta, from the crust down into the lower crust and the upper mantle. And so we have a pretty good idea of what Vesta is made out of. So that's all happening at the south pole of Vesta. But the north pole of Vesta seems to have these interesting highlands that things almost seem to be piled up like a big mound of dirt. Similarly to what's found on the far side of the moon, aside from the South Pole Lake and Basin, there's an anomalous highland. And it's not really clear how these formed. Some ideas have been that it's a result of those basin-forming impacts in the south, which could have caused ejectode overlap or to push the North Pole out a little bit. But there's a recent paper that came out where they're looking at some of these meteorites that have fallen on the Earth. There's a special class of meteorite called a mesosiderite. And forgive me, I'm not a geologist, but I believe these are the ones that are thought to come from the core mantle boundary.
Yeah.
And what that means is they came right from the part where you have this nice warm mantle material right next to the metallic core of Vesta. And so there was this team that took some of these meteorites and tried to look at some of the isotope ratios, trying to figure out how old these pieces were. And the idea with isotope ratios is that with some, most things that we think about on Earth are stable. You look at a banana and it's got potassium in it, and potassium is usually thought to be a nice stable compound. But it turns out some of the potassium is radioactive.
You can detect bananas with Geiger counters.
Yes, you can. And it turns out if you have old Fiesta ware with the orange glaze, that actually has some uranium in the glaze, and you can actually detect that with a Geiger counter. Again, it's not enough to be harmful, but it is present. And these compounds break down in a known way. And so if we imagine that we take some of these radionuclides, as they're called, and we stick them in a box and don't let anything escape, and since we know how quickly they break down, we can just measure what's there and figure out how old it was. We can figure out when these particles got locked in that box. And so the idea is, when someone talks about the age of a rock, what they're talking about is when that rock solidified, when that box formed around those radionuclides and didn't let anything out. And different isotopes condense out at different temperatures. And so if you do a suite of studies on one of these objects, you can actually find that different things formed at different times and that different parts of the rock formed at different times as well. When they were looking at these meteorites from presumably Vesta.
And here I'm going to cut in because we have folks wondering, how do we know which meteorites we collect on Earth are from Vesta, from other asteroids, in particular from Mars, from the moon? How do we look at an individual meteorite and figure this out?
That's a really good question. When something comes from the moon, it's kind of easy just because we have pieces of the moon that the Apollo astronauts brought back, and so we can look at what they're made out of. Specifically, you look at isotope ratios, how much, for example, a common would be carbon-12 versus carbon-14. That's not necessarily what we look at, but people are familiar with radiocarbon dating. Those are the types of things you're looking at. The Earth and the Moon have very similar isotope ratios. And so if we find a meteorite that came from the moon, well, when we look at it, number one, it looks like it's a piece of the moon. It looks great. But more importantly, in a laboratory, you can see that it's actually made of the exact same stuff. And so we know that one. With Mars, it's a little harder because we don't necessarily have known pieces of Mars to compare it to. But spectroscopically, you can compare and see that it has the same minerals that are found on Mars.
It's reflecting the light the same way.
Right. Yeah. And so we know that it can have the same minerals, and we know what minerals are on Mars because we send robots to Mars to look at these things. And very interestingly, sometimes these meteorites have trapped gases in them. And so we can sample those gases and say, hey, this perfectly matches Mars's atmosphere. And so there's ways to do it. With the HED meteorites, it was suspected through the spectroscopy, which wavelengths of light do these asteroids and do these meteorites absorb, which tells you what minerals they're made out of, and they look to be more or less the same. So when we look at HED meteorites, we know that they came from Vesta. And so when they're analyzing a piece of Vesta, and you're looking at it, if you're analyzing an HED meteorite, you're analyzing a piece of Vesta. So some of this recent work just tried to figure out, when did these rocks form? And what they found is that there seems to be two different times when these rocks solidified. They found one that happened at 4.56 billion years ago, and one that happened at 4.5 billion years ago. And those are pretty close. And coincidentally, that's not long after the formation of the solar system, about 4.6 billion years ago. And so what this paper is claiming is that these two different ages are suggesting that there was what they call a hit and run collision, where Vesta got hit by something big, and it sort of was a glancing impact. It scraped and collided with the north of Vesta, and presumably, and their claim that's what formed those north end highlands. Now, that is quite a provocative claim, especially based on isotope dates. But nonetheless, with the scientific method, it is actually testable. And one way to actually test if such an impact could form those highlands on the north side would be using computer simulations. So nowadays, we have computer codes. They're called, the fancy term is hydrodynamic shock physics codes, or hydra codes for short. And what that means is they're really good at simulating how rock behaves when it hits other rock. And so in particular for planetary science, they're great at simulating impacts, hypervelocity impacts, things that are happening at tens of kilometers per second, which for context is 30 to 50 times faster than a rifle bullet. I mean, just unimaginably fast objects. And so presumably, if this is what formed then the lunar the Vestan Highlands in the north, you should be able to recreate that with an impact code. So I guess the challenge is on for anyone who wants to do that.
And this is the kind of situation where it takes a lot of different people running a lot of different code to confirm something in software, because any of us who've written software before know, wow, I just broke the universe because I misspelled this one variable over here. And it's through doing different software that recreates the physics over and over that we're able to get down to, yes, this seems to be exactly right. And they've started doing a model. They have the basic pieces of object hits Vesta, probably changed its spin axis. We haven't talked about that. It wasn't that there was an impact exactly in the South Pole. That would be terrifying. It's that the spin axis probably changed. And what became the South Pole of Vesta, the material it tossed up, just like the material that got tossed up when the Earth got hit, well, it had to settle down. Here, when Earth got hit, it formed the moon. With Vesta, when it got hit, it formed the Northern Highlands. Is that a good way of looking at this?
So it's a little bit more complicated. So the impact that is at what is now Vesta's South Pole happened much more recently than this paper claims. That happened maybe only 1 billion years ago, which I know is a long time ago. But over the age of the solar system, it was relatively recently. This new work is claiming that the North Polar Highlands are actually 4.5 times older than that. That when the North Polar Highlands formed, Vesta wouldn't get hit by that basin-forming impact for another 3.5 billion years. So that's but what you were saying before with combining these different techniques, planetary science is unique in that it involves people from all sorts of different backgrounds. My background is in physics. You have geology backgrounds. You have chemistry backgrounds. And all of us are working together to solve different parts of the same problem. And when someone thinks they figured one thing out, someone else can come back and say, well, you've got to be able to explain this other aspect of it. A great example of this would be on Ceres, is the largest dwarf planet in the solar system. Not the largest dwarf, sorry, the largest dwarf planet, well, the only dwarf planet in the inner solar system. It's the largest asteroid in the asteroid belt.
It's the OG former planet. It was a former planet more than 70 years before Pluto was discovered.
Correct. Yeah, when Ceres was discovered in 1801 by Piazzi, it was thought that, hey, we have found the missing planet between Mars and Jupiter. So we've all of our ideas about the structure of the solar system do actually work, because we've been looking for this planet forever. The problem is they found another one right away, and within a few years there were 6 known planets orbiting between Mars and Jupiter. And it didn't take too long before someone realized, hey, maybe these are actually part of a bigger belt-like structure that we now call the asteroid belt. And when Pluto was found, it was actually, the problem with Pluto was almost that we didn't find another one for decades afterwards. If we'd found another Kuiper Belt object, say Orcus, or something else that shares Pluto's orbital space, we would have recognized much sooner that, hey, it's not alone. But with Ceres, it is bigger than Vesta. It's water rich. And recently, and this was the second target of that Dawn spacecraft, that found a whole bunch of interesting things on Vesta. One thing they found were evidence of hydrothermal plumes that were putting a bunch of minerals on the surface that looked like they were dissolved in water. And more recently, in fact, just this year, I believe, someone was looking at gravity data of Ceres and found evidence that, hey, there's something below the surface that seems to correlate with the largest mountain on Ceres. They think it's actually a plume of water that is rising through the crust of Ceres, and it's pretty large. We're talking.
This is Ahuamans.
This is Ahuamans.
The sheer edged mountain that appears at the bottom of a large crater. There's a release last week talking about how it's thought to actually be a mud volcano.
Yes.
It's awesome.
Right.
Carry on.
So, and so you can have evidence from geology and chemistry saying we think these processes are happening. And then someone can look at, Newtonian gravity, physics, and say, hey, we have found that the excess or lack of mass below Ahunaman seems to be pulling the spacecraft in weird ways. And we can detect it because the Doppler shifted the radio signal. And so we know that the spacecraft is moving weirdly than if this wasn't there at all. And it turns out there's probably a giant plume of water right below Ahunaman that could be feeding this mud volcano.
And that is fabulous. And our solar system keeps showing that there's science that's far more complicated and interesting than anything we previously imagined. And this is also showing the power of what we can do with computer simulations to understand the inner workings of these worlds we can't go out and touch. So Jordan, if we wanted to prove any of these different theories, ranging from, yes, there is a large body of water under Ahuamans, to, yes, it was this dual impact that created the basin and the crater on the south pole of Vesta, with one of those two impacts leading to the highlands. How do we go about proving these different theories?
So, proof is really a hard thing in science, right?
Yeah.
It's almost impossible to prove that something doesn't happen. The best you can say is, I'm as sure that this didn't happen as I'm sure that if you walk off the edge of a cliff, you won't fly. The best way to do it is to say, hey, we have a story that seems to fit with all of the other data. It's what we call falsifiable. You can come up with an idea, and it seems to explain something. Say it explains both the basin on the south and highlands on the north. And what you need is to find something that doesn't agree with that. Either saying that the highlands in the north had to be older or younger, or that you just don't get the right, say, gravity signature, or you don't get the right minerals, or whatever it happens to be. In the case of the moon, if we're going to go back to that, there was the where we think we found these authors think they found the core of this giant asteroid that hit the moon and formed the South Pole Aitken Basin. One question would be, how much material is there? Does it agree with how big one of these cores would be? And one of the tricks is when iron hits the mantle, it breaks up into smaller droplets. And if they're too big, they're not going to stay in the mantle. They'll sink all the way to the core. And so you can say, hey, they have to be smaller than, say, 25 kilometers or 16 miles across. And if we add them all up, do we get the right amount of stuff? Is one way to do it.
And it's this slow and steady brainstorming and figuring out, how do I both prove this and disprove this? And doing both. That is what allows us to slowly move our science forward, occasionally with two possible scenarios. And here our audience is starting to ask both of you questions. And I see Alara Sophia is asking, I was wondering why Dr. George thinks the theory about cumulates being the mass in the moon is not as likely.
Sorry, I muted myself just to be safe. Okay. So let me see. I wrote that part down. Right. They, because of the models, they are saying that this mass has to be 300 kilometers deep. And the cumulates that I was talking about would probably be at the most 100 kilometers deep and probably shallower, actually. So that's a big ruling it out.
It's all about the placement.
And if I could jump in on that.
Please.
Yeah, one of the other pieces of evidence is that this gravity signature over the South Pole Aitken Basin is in the middle of the South Pole Aitken Basin. If you had a mantle plume, there's no reason to think that it would happen to just come up in the middle of the largest basin on the moon. So the fact that they are geographically co-located it doesn't necessarily prove that they are of the same event, but it is strongly suggested that they are. And so if you have two possibilities, one is that this just happens to be a plume that by happenstance is co-located, and another one that says, hey, we formed this massive basin, and by the way, we think we found a piece of the thing that made it still below the surface. That's a much more compelling story.
And we have a couple questions about how we tell this story coming in from Hexacasacoron. I'm sorry, Noel. I'm just going to use your real name. The first one he asks is, are there any processes that can reset the isotopic ratios? And are there any examples on Earth where higher density crust points to impact craters?
So I guess I'll jump in on this one. With isotope ratios, now granted, I'm not an isotope chemist by any stretch. But from what I understand, the way you reset it is you have to open the lid of the box. You have to somehow break open the structure that's containing these isotopes. Now, this was in something called the zircon, which are particularly resilient and very strong. And as a result, some of the oldest pieces of the Earth's crust that we have are actually zircons from over 3 billion years ago.
This is essentially a gemstone.
Sorry?
This is essentially a gemstone. It's a crystalline mineral.
Yeah, it's a crystalline mineral. And so one way to reset them is to, melt the mineral. So one way to do that is hit it with something else. When the moon was formed, the Earth got hit by something the size of Mars and turned the Earth into a molten ball of magma. That would certainly reset anything that's molten.
Can I jump in here?
Yeah, please.
So zircons are very resilient. And they say diamond is forever. A zircon is forever, actually. It is really hard to melt a zircon. And if you are finding zircons that are coming up at the age of the solar system, you can believe them.
So does this mean theoretically that if someone has a zircon ring, a geoscientist could tell them how old that rock in their ring is?
Yes.
If they let them drill it up a little bit and have the right equipment.
Yeah. And actually commenting on that, diamonds are not forever because diamonds aren't stable at the surface of the Earth.
Yeah.
Diamond is a piece of carbon that forms a crystal under high temperature and pressure. Once you remove the high temperature and pressure by bringing it to the surface, it slowly turns back into graphite.
So right.
So everyone's engagement rings are going to turn into graphite someday in the fullness of time?
To be more accurate, diamonds are not forever. Diamonds are for a long, long time.
True. True.
So going back to the other question, do we have pieces of higher density crust on the Earth? We do. A good example of this would be in Canada, in Ontario. There is near Sudbury, Ontario. There's what's called the Sudbury impact structure, and it is there's this fight back and forth over where the truly largest impact structure that remains on the Earth is. And one of the problems with the Earth is that 3/4 of it is water. And if you have an impact into water, all you got to do is wait for plate tectonics to subduct that crust, and your impact structure is gone. So we do have a few that hit the land. And the one in Canada is 350 to 400 kilometers in size. I can't remember if it's radius or diameter, but it's massive. And it's big enough that when this object hit, it would have punched a hole all the way through the crust and splashed up some mantle material. And it turns out that when someone was surveying this area for mines, they found a whole bunch of nickel and all sorts of other useful minerals that ended up on the surface of the Earth because of this impact. And so because of that, Sudbury's an example of nickel smelting today.
And wasn't the Chicxulub crater in the Yucatan Peninsula originally identified due to oil people making gravity measurements at the surface?
Yes. There was oil exploration companies in the Gulf of Mexico. One of the ways you look for oil is to use gravity probes. You look for, and the great thing about gravity is that the more stuff you have, the stronger your gravity field is going to be. And oil is less dense than rock. And so what they were looking for is little gravity anomalies that suggest there's less stuff below you, suggesting that, hey, there might be oil there. And what they found using these with very precise measurements is that there's this ring of this strange gravity signature that seems to be nicely located just right off the Yucatan. And but it wasn't known for a while because this was industry's information. They wanted to keep this under wraps because if they found oil, they didn't want to let everyone else know that there's oil there. And so it took a while for the scientific community to know that, hey, there's something weird going on there. And it turns out that, yeah, it is the impact structure that knocked out the dinosaurs 66 million years ago.
And I got my hands on one of the gravity probes that they use at one point while at a conference. They were trying to sell them, and I was like, hey, this is cool. May I just look? I will never use one of these. And the guy was bored. And they can actually measure the difference in gravitational pull between your feet and your eyeballs. And so you can kneel down and stand up and see gravity change for the probe as you stand. So these are very sensitive measurements. And it's kind of awesome. Play with one of these if you ever get a chance. I'm looking to see if we have any more questions. Pardon me while I scroll. So one of our diligent Bennu mappers, Rukoda Presents, is asking, have the two of you pitched in to help us map the asteroid Bennu for the little OSIRIS-REx spacecraft?
I have not. I'm sorry.
It's okay. You're sciencing. You're doing other sciences.
Well, yeah. Okay.
I also must admit that I have not. I'm really interested to see everything that's coming out of the OSIRIS-REx mission. The fact that the asteroid Bennu is just throwing rocks out into space. I mean, it's hard. So it's hard enough trying to get a piece of. So the whole point of OSIRIS-REx is to bring a sample of Bennu back to the Earth.
Yes.
And it's hard enough to find a safe landing spot just when there's a bunch of jumbles of boulders everywhere. But when the asteroid's firing back at you.
Yeah. And when you initially expected something that looked kind of like Itokawa with a few nice smooth regions, and instead you get a gravel pile. My hat's off to all the over 5,000 people in our community that are plugging away. The last of our images went in today. So we have 4,500-ish images that each need to be marked by 15 people. And I was showing them earlier that the data is coming out good. So we're super pleased with what we're seeing. But you guys are doing other science. Keep sciencing. That's all that matters, is that everyone makes a science.
I must say, I appreciate everyone who helps out on platforms like CosmoQuest to help us out doing science. We really can't do it without you.
And our community, I don't know where you get all the dad humor, because not all of you are dads. But our instro just put in kibbles and rocks and rocks and rocks. Yes. So I'm not seeing any more questions. So if people wanted to learn more about the work the two of you are doing, where can they look? Jordan, I'm going to start with you.
Well, one way is to just Google us and find some of the work that we've done. some of that's going to be scientific literature, which might be which can be hard to parse. But I know I've done some interviews where I present this a little bit more broadly and put it in context so that it's understandable to non-specialists. And if you're really interested in some of the work that's happening, you can always go to our institutional website, Planetary Science Institute, which is psi.edu, and you can see what different people are working on. We've got people working on, we really work across the universe.
Yeah, it's true. It may be Planetary Science Institute in the title, but you have me, the database big data person who does variable stars when not counting craters. So George, where can people find you on the internet?
So yeah, I guess in general, I would have to say maybe on the PSI website, you can find some stuff about me. Another thing is that I started a group called the Female Superheroes of Science. And we do have a Facebook page. I really encourage you to find it and like us, because we still have to make so many likes to get a handle. And, but we go around. Currently, it's just the Houston area, and do outreach events. Talk at schools. We did we've been at Comic Palooza before, and we actually would really like to have more people across the country and across the world to join us. We are called the Female Superheroes of Science. We do not exclude engineers or mathematicians. You are also welcome to join us. And we would love to have you.
And Susie Murph, thank you. Susie just dropped the link into the chat. So all of you click on over after the show is done or in a different window, please. Click on over, give them a like, and find out more.
Thank you.
Thank you both. This has been fabulous. And thank you, audience, for being here. Once again, this has been The Daily Space. We are a production of the Planetary Science Institute, working in collaboration with Youngstown State University. We are brought to you by you. Thank you to all of the generous people who have made financial contributions. And there are so many other ways you can support us other than money. We need that. That's how I pay people's salaries. But beyond that, get the word out. Go do some science. Mark rocks, mark boulders, mark the occasional crater on Bennu. And tell your coworkers, tell your friends, tell your enemies, tell everyone. Go help us explore our universe. We are your place to learn and do science. You can find us most Mondays through Fridays at 1 p.m. Eastern. That is 10 a.m. Pacific, 6 p.m. London time. Tune in. It will be me or Binary Blaze. We will be taking the week of 4th of July off. But other than that, expect to find us here. And on Sundays, Annie does the Sunday Science Hour. She is currently working her way through colorizing Spitzer data to show you how we go from the images that come from the spacecraft to the beautiful things, well, you see on this show and in all the shiny magazines. Now, I am going to ever so awkwardly, because this is the only way we know how to do it, I'm going to ever so awkwardly roll the credits and find someone to raid. Once again, thank you, George and Jordan. Having you two here, I was in over my head, and you guys really, well, helped this go swimmingly, to use the dad puns of CosmoQuest.
It was fun. Thank you.
Thank you.
So here we go, everyone. Here are the credits, and maybe, working on it. Wherever you are in the world, have a fabulous morning, evening, or afternoon, and our software to roll the credits is saying no. So I'm just going to have to thank all of you myself. Thank you, mods. Thank you, subs. Thank you, follows. Thank you, everyone who makes this show go. I don't have cover of credits to find someone to raid, so I'm now going to awkwardly find someone to raid. Hello, awkwardness. Oh, bother, please be on. You are not. Adam, please be on. You also are not. If anyone can suggest... There he is. Adam is going. We're going to raid... Oh, we're going to raid Sky. Sky is here. So, Give Skylius a giant CosmoQuest welcome. Light up her chat with rockets and rove on with that little opportunity rover. I will see you tomorrow. And wherever you are in the world, remember, have a fabulous morning, evening, or afternoon, and get outside and look up. Thank you. Bye-bye.